Welcome, everyone. Welcome to the first AAAS-AMS invited address at the joint math meetings of 2022. It's been pretty complicated with COVID and a bunch of other problems that have come up, but we have made it. So it is a great pleasure for me. My name is Ken Ono, to introduce the inaugural AAAS-AMS invited address. As a former vice president of the AMS and retiring chairman of the mathematics section of the American Association for the Advancement of Science, I'm delighted that under my watch, these two organizations have come together in this joint venture. Founded in 1848, AAAS is the largest scientific society in the world, with over 120,000 members. AAAS is well known. It's well known as the publisher of the scientific journal Science. AAAS might not be so well known to many members of AMS, though, as Science doesn't publish many articles in mathematics, but AAAS is very important to mathematical scientists and all scientists in general. You see, AAAS seeks to advance science, engineering, and innovation throughout the world for the benefit of all people. I'd like to point out that former AAAS presidents have been mathematicians. Maybe the names Simon Newcomb and Joseph Lovering ring a bell. They were two presidents of the AAAS who were very important mathematicians. So what are we aiming to do here today with the first AAAS-AMS invited address? Well, the goal is to spotlight a prominent mathematical scientist who epitomizes and shares the AAAS-AMS joint mission. And what is that mission? The mission is to advance the goal of mathematical sciences for the benefit of mankind. This can be done in many ways. So when we were coming up with the idea of the address, we wrote out some examples of what such a mathematician would aim to do with this lecture. We wish to enhance communication among scientists, engineers, and the public. We seek mathematical scientists who promote and defend the integrity of science and its use. We wish to strengthen support for science and the entire technology enterprise. We want to provide a voice for science on societal issues. We want to promote the responsible use of science in public policy. We wish to foster education in science and technology for all. We wish to heighten public engagement with science and technology. And of course, we want to advance international cooperation in science. And with these goals in mind, the committee had a unanimous choice to be the first AAAS-AMS invited speaker. So it gives me great pleasure to introduce Kavita Ramanan, the Roland George Dwight Richard University Professor of Mathematics at Brown. She has had an incredible career. The last few years have been very exciting, an exciting period for her. When it rains, it pours. In 2019, she was elected AAAS Fellow. She has recently been named a Fellow of the AMS, a SIAM Fellow, recently elected member of the American Academy of Arts and Sciences. And in 2020, she was awarded a Guggenheim Fellowship. And that is just to name a few. I can also add that Professor Ramanan and I both appeared in a documentary about the Indian mathematician Srinivasa Ramanujan. So maybe Professor Ramanan could add to her CV that I have Ramanan number 1. So without further ado, it gives me great pleasure to introduce Kavita Ramanan, and she will deliver a lecture entitled Interacting Stochastic Processes on Random Graphs.
Start by saying I'm deeply honored to have this privilege of giving the first joint lecture as somebody whose views align very closely with that of AAAS, having participated in many marches for science and also passionate about outreach, as well as the AMS and its attitude towards scholarly publications. I'm deeply, deeply honored to have this privilege to share with you a little bit of my research on interacting stochastic processes on random graphs. So about this talk, it focuses on the study of stochastically evolving locally interacting particle systems, which arise as models of many physical phenomena, whose dynamic interactions are governed by an underlying network structure, which itself may be random. In that sense, I mean that the stochastic evolution of each particle is directly going to be influenced only by the states of neighboring particles in the graph. So I will make clear this as we go along, but the overarching theme when trying to understand large aggregates of stochastically evolving collections of entities or particles is to try to understand such dynamics and obtain rigorous limit theorems, since these dynamics are not tractable, not amenable to an exact analysis. The goal, rather, is to try to find principled approximations that can be justified by rigorous limit theorems that allow us to gain insight into such systems and to beat the curse of dimensionality in such high dimensional systems. So in this talk, I will briefly describe, of course, introduce what I mean by these particle systems, where they arise, and then tell you a little bit of what was well known, what was not well understood, and some recent progress on the latter. So I will start with some illustrative examples, motivating examples from applications. So, and unfortunately, topical model is that of a spread of virus, which could be actually the virus or cold of a disease, or also a computer virus. So you might have some particles or individuals' computers, which are represented in terms of indexed by nodes on a locally finite graph. And just say a finite graph for the case, for the present. And there is a very toy model of the spread of viruses, which is called the contact process, where each particle simply takes one of two states. It's either 0, which represents healthy, or 1, which represents infected. And healthy particles are infected at a rate proportional to the number of infected particles in their neighborhood in the graph. So in this case, you have this infected particle, which has the scope of infecting its neighbors here, these two neighbors. And infected particles recover at some constant rate and get cured. And then they can again, once again, if they have an infected particle in their neighborhood, can again be susceptible to getting infected once again. Whereas healthy particles are infected at a rate proportional to the number of infected particles in their neighborhood in the graph. So to describe this discrete time contact process more clearly, we can fix a graph with some vertex set and some edge set, which is some subset of unordered pairs of vertices, in which I will always assume that there are no loops, so that you never have two coincident vertices as part of an edge. And then we will use this little twiddle to denote that U and V have an edge between them. And dV will be the sort of degree of the vertex of a graph. So the contact process is simply a process which takes values in 0, 1 to the V, which each particle xv at some time t will just be taking values in 0, 1. But it's a random process. And how does it evolve? So at time t for each V and V, each particle, if it's in state 1, will transition to 0, which is a healthy state at some constant rate. So there's some parameter q in the model. And if it is 0, then it will transition to 1, either proportional to the fraction of infected neighbors, or in some models, you can say that it will be proportional to the number of infected neighbors. Okay, so this is the discrete time contact process. There are many, many variants of this model. So instead of just having healthy and infected, you could also look at another state where if you have a particular disease where once you recover, you become immune, and so you are not susceptible to getting the infection again, and that is called the SIR process. And once again, now you have 3 states, and your transition from S to I is just proportional as before to the fraction of your infected neighbors. And then when you go from infected to recovered, like you're a green vertex, you can never go back to being infected or susceptible. You remain that way. So you just have this sort of particle system where more and more people are just getting into the recovered state. And so the questions that you'd be interested in asking, maybe how long do you take to get to this fully recovery state? Or if you're in the contact process, how many times will a particular individual get reinfected? What is the fraction of individuals in the population infected at any time? How long does it take an epidemic to die out, if it does die out? How does this depend on the interaction graph structure? So there are many such questions that one wants to ask. And all of these discrete time processes that I mentioned are just examples of what is more generally called synchronous Markov chains or probabilistic cellular automata, which given a graph and some state space S, you, for every V or XV of t, denotes the state of the particle V at time t, and which takes values in this state space S. And the evolution is simply, you can think of it as sort of this random recursion. So that at each time, XVT plus 1 evolves given some transition rule, F, which depends on its current state, XVT, the states of its neighbors, and then some random noise, which we represented in the last description in terms of these probabilities of flipping. But it can always be written in this way in terms of a random recursion. So while these probabilistic cellular automata do arise in some models and they're interesting, there's also a good reason to look at more continuous time models, which are sometimes a better capture certain phenomena. So one could do, of course, a continuous version of both the processes that I mentioned, but I will share yet another model that one has. That is of opinion dynamics. So once again, something which is very popularly known as the voter model. It's again another toy model of opinion dynamics, where the state of each particle is again in, let's say, in 0, 1, which could represent two different opinions. And so the sets of transitions of each particle, just like in the contact process, it can either go from 0 to 1, which is then a positive 1 jump, or it can go from 1 to 0, which is a -1 jump. And now you have to say sort of what are the rates at which you make these transitions. So since it's in continuous time, each particle after an independent exponential time with a certain rate will poll one of its neighbors at random and adopt their opinion. So these rates tell you sort of how frequently this happens, and the rates in particular directions, either from 0 to 1 or 1 to 0, depends on just for particle V will depend only on the configuration in the neighborhood of V. And so that's where the sort of locally interaction through the graph structure is relevant, that the rates in general could depend on the entire configuration, but we're saying that it only depends locally through the graph structure of the states in the neighborhood of the graph. And so this is just restating what I said earlier, that the chance of moving from opinion 0 to 1 is just going to be proportional to the rate at which you do that is proportional to the number of neighbors that you have with the opposing opinion. Okay, and you can have many, many versions of this model. You can say that it's not that you're going to adopt an opinion. You could adopt the opinion with some probability, or you look at sort of the majority of everybody in your neighborhood and adopt that opinion rather than just one at random. So there are many versions of these sort of models. These are just to give you some idea of the kinds of dynamics, what kind of models we will be including in our consideration. Another quite different model arises in studying spike trains of neurons. So spike trains are simply just the firing times those, in a particular neuron. So if you have just one neuron and you have this stochastic process xt, which represents the number of firings of the neuron in the time 0t, you have to say, okay, what does the time of the next firing depend on? And it turns out that the rate doesn't just depend on the current state of the neuron, but it depends on the entire past of the history of the spike train in a certain, very structured way, which is this conditional rate given the history of the spike train is equal to some suitably nonlinear function of the sum of some constant input and some convolution of the history of the spike train with a certain filter. So the details are not important, but the only thing I want to emphasize here is you can also have models where you have sort of here, it's a very simple model that I'm taking. The real neuronal models are much more complex with, sort of excitatory neurons, inhibitory neurons, etc. But these, I'm just giving you very, very toy examples to try to illustrate what kind of models we can include. So you have the particular feature of the neuronal hawks, which was not there in the previous two models, is that it's really non-Markovian. By Markovian, we mean that the current evolution only depends on the current state of the whole process, whereas here it actually depends on the history of the process. And in particular, when you look at these neuronal hawks models, you can look at them on networks. So again, now you have a graph and you have neurons at these different vertices firing, and then the firing rates, again, as before, these firing rates are some nonlinear function which ensures that the rates are non-negative, are again given by some constant input to that vertex, plus some convolution of the past, but not only of its own past, but also of the vertices that are pointing towards it. So in this case, there's not necessarily an undirected graph. You don't have necessarily symmetric interactions, but you might have some cases of a directed graph structure. Okay, so this is one motivating example. And finally, for a completely different kind of dynamics, you could also look at sort of systems which are diffusive. So if you want to look at what are called sort of coupled oscillators, which are again sometimes proposed as models of neuronal dynamics, one thing is called the Kuramoto model. So this is the stochastic Kuramoto model, in which you have a certain drift, which this xv represents the phase of the oscillator at site v at time t, and you have a certain drift which is given by this sine wave of the difference of the average of the sine of the difference of the phases between you and your neighbors, and then some constant drift additional, and then some Brownian noise, independent Brownian noise at each of the vertices. Okay, so these are all sorts of models that arise in modeling various physical phenomena, and they all have the common property that they are networks of locally interacting stochastic processes. So you have a finite connected graph, a state space S, and we want to look at stochastic processes evolving where you have this collection of XVT, V over the vertices of the graph, and T evolving with time. And the state XV of a node may evolve, like I showed you, as a discrete time process or a continuous time jump process in some discrete space, or as a diffusion. But the main point is that the instantaneous stochastic evaluation, the transition, the immediate transition, or the drift in the diffusion case, or the jump rates at any time will depend only on its own state history and those of nearest neighbors in G. So locally refers to local with respect to the graph. And I will henceforth, sort of just to keep a concrete model running throughout, talk about this running example of this diffusion, which is just a slight generalization of the Kuramoto model, where now I'm allowing any kind of pairwise interaction. It doesn't have to be the sine function. I will always assume that the pairwise interaction function is nice and regular so that the stochastic differential equation is well defined. And this, of course, can be just informally viewed as a sort of ODE system on a graph perturbed by some Brownian noise. Okay, so what are the questions of interest? So we really want to understand how these large aggregates of collections of stochastically evolving particles work. And as I mentioned, you cannot analyze them exactly. So one always wants to look for approximations. And since these are large, you want to understand when the particle size goes to infinity, can you describe the limiting behavior of any typical particle? So in all the examples that I gave you, there's a lot of symmetry in the sense that the identity of the vertex doesn't really affect how the dynamics is. So the dynamics is the same viewed from any vertex. Of course, it will depend on the neighborhood structure, but it doesn't change beyond that. And then in the sense that these drift coefficients don't depend on V. And so there is this notion of a typical particle, which I'll make even more precise as we go along. But so you want to understand what is the dynamics of a typical particle for large n. Is there a way to understand it without saying that it is sort of the marginal dynamics of a very, very large system, which is much harder to get your hands on? And another quantity of interest, which is useful to answer some of the questions that we mentioned earlier, is what is called the empirical measure of the particles, which is simply here delta x denotes the Dirac delta mass at some point x in R. And this is just simply the average of all the Dirac delta masses of the state of the different vertices, okay, and over the vertex set. Okay, so you want to understand the random empirical measure of these particles. And then you might ask, okay, this is a complex system, and why would you even expect that they should have some limit? I mean, there's just some graphs and their sizes are going large. So one question is, why would you expect such limits to exist? So for that, I'm just going to do a very brief review of some classical limit theorems in probability, which goes back to, let's say, the classical strong law of large numbers, which is probably well known to most in the audience, which sort of the weak version starts with Khinchin in 1929, with, of course, precursors by Bernoulli, Markov, Poisson much earlier, and Kolmogorov in 1933. And it simply says that if you're given some independent and identically distributed random variables, or if you prefer, you can think of them as measurable functions from some probability space, real valued with a common distribution, nu, for which the vector is just given by the product measure. Then it says that the average of these, or the empirical mean of these random variables converges to the expectation or the sample mean, which is just this integral x nu dx. Because so this is known that this limit happens with probability 1 or almost surely. So this is very well known. So what does that got to do? Well, it says that somehow when you have independent aggregation or aggregation of independent things, it leads to some predictability and some deterministic limits. But you can have more general strong laws of large numbers, which may look a little more relevant for what we're looking at. And so I would just like to say that if you're given a measurable space, and PS is the space of probability measures on that space, equipped with the topology of what probabilists refer to as weak convergence, which simply means that mu n converges to mu if for every bounded continuous function on S, you have fx mu n dx converging to fx mu dx, sometimes referred to as weak star convergence. Also, let C denote the polar space of real valued continuous functions. I'm interested in these because the trajectories of Brownian motion and diffusions take values in this space. And I'll always equip it with the topology of uniform convergence on compact sets. And so it makes sense to also talk about probability measures on this space with the corresponding Borel sigma algebra. Okay, so now we know that the classical SL said this. And again, once again, I have these IID random variables with distribution mu. But we were interested in sort of empirical measures of our processes. But first, we can say, suppose you have empirical measures of just these random variables in R, then what do we know about that? So these are all independent. So if you look at the average of the Dirac masses at these different random elements, so now nu n, remember, is a measure that is random, and it's a probability measure in R, but it's a random probability measure in R, and that's converging to the law of the particle, which is just nu by our definition. That also holds true almost surely. So we know that even when you have Dirac delta masses, that converges to a deterministic law as well. Okay, so that's good news. And another way to interpret this is just to say that the proportion of, this is a slightly stronger fact that holds due to what's called the Glivenko-Cantelli theorem, but that the proportion of random elements that are less than or equal to any real number will also converge to the nu of minus infinity. It should be nu. Okay. But now let's get closer to something that we're interested in. Now you have independent Brownian motions. In other words, that Brownian motions are just such that the image measure is what is called the Wiener measure, right? So their law is the Wiener measure. Then you might ask, what is the empirical distribution of IID Brownian motion? What will they converge almost surely to? And it turns out they also converge almost surely to their law, which is Wiener measure. Okay, so these random now, mu n is a random probability measures on the space of trajectories or continuous functions, and that converges by the strong law, by a strong version of the strong law to the Wiener measure. Okay, so all these classical theorems tell us that an aggregation of many independent entities in very different situations is well approximated by a deterministic quantity in the limit. But recall, we're interested in sort of really interacting dynamics, and these classical theorems yield a limit only in the trivial non-interacting case when B is equal to 0, then XV is simply Brownian motion. And then if you want to look at the empirical measure, that will go to Wiener measure, but that's not interesting at all. We're really interested in the interaction and how this interaction through the graph structure really affects all the dynamics. So, but this gives some idea of why you might expect that, okay, there are situations in which you might have limit theorems when you have aggregations. So remember these key questions. You have this these interacting diffusions, and you want to ask what's the dynamics of a fixed or typical particle, and also what is the limit of the empirical measure of these particles, which is once again defined like this. Now, if Gn is equal to Kn, which is the complete graph on n vertices, which is you take n vertices and it has all edges of all distinct vertices are connected, then I'll just denote this xkn by xn, which is the solution to the SDE on the graph kn. Then, of course, I can label the vertices 1 to n, and then my this system just reduces, it can be rewritten in this way. Okay, so one thing to note here is that these are weak interactions, because if you look at as I said, we can assume that B is sort of bounded. So then the effect that any one neighbor, xk, has on xi is really 1 over n minus, of order 1 over n minus 1. So while they are interacting, there is sort of, at least in the drift term, you can see that the interaction is weak because it's going to diminish. The pairwise interaction is going to diminish between any one vertex, is diminishing as the size of the system n gets large. So you might expect that there might be limits in this case too, because we know that there is in the non-interacting case, and so maybe there are some in the interacting case as well when it's sufficiently weak. And indeed, this is a classical result, and so it's known that when Gn is Kn, these particles interact. I'm just rewriting this dynamics here, so you have it here. Then we can reformulate this dynamics in the following way, where dxi, I'm just rewriting this as an integral with respect to the something that's almost the empirical measure. Okay, so this is really a little bit, because it's 1 over n minus 1, and this k is missing. There's a dependence on I. But so bxm is just this integral that I have, which is just another way of writing this drift term. Okay, but the nice thing to know is when B is bounded, then you know that you have some sort of continuity with respect to the measure of the capital B, which is this drift. Okay. So recall this dynamics, and now I can rewrite this dynamics in this way, where this mu in is close to being the empirical measure of the system, but not quite. But it's only missing a delta mass, which is given weight 1 over n. So you expect that to not matter in the limit. And indeed, so you expect this mu in to be more or less the empirical measure for every n. And if you think that weak interactions would also yield a deterministic limit, just like the case of no interactions, then you would expect mu n, this can be replaced by mu n instead of mu in, and then mu n will converge to mu, which was some deterministic quantity that one still has to find out what it is. So it's mu of t. Then by continuity of this B, you might expect that the dynamics of a typical particle, you can just replace this mu n by this limit mu, and that's what you would expect to be your dynamics of this typical particle. And indeed, this is classical work that goes half a century ago. And you also know that as we saw earlier, that when you have weakly interacting or sort of independent random variables, then in fact, the limit mu t is really just the law of any one of these particles. And here we know all these particles are exchangeable in the sense that they look the same. They're almost identical in the way that their dynamics. It's a homogeneous system. So you can see that the mu of t is actually going to be equal to the law of the law of xt. So of course you have to prove this, but this is all very reasonable given what we know about the non-interacting case. And so you have this sort of closed system here, which is quite remarkable because you have this really high dimensional system and you want to understand the dynamics of just one particle. You actually have to run the entire system and then understand what this dynamics is doing. But what this beautiful result says is that at least for large n, you can approximate it simply by an autonomous equation given by this. So you can just look at the dx of t being with a drift that is driven by its own law. And so this, you can show that this SD is well defined. It's an inhomogeneous Markov diffusion, which one can say a lot about, and I'll say a little more later. Okay, and then one might ask, okay, that's for the complete graph, but I'm sure there are many models in which not everybody is interacting with everybody and you don't have so much regularity. So you might ask what happens when you have dense graphs. And so, you know, what do I mean by dense graphs? And I really mean by sequences of graphs whose degrees all go to infinity. So they might not be, you know, the degree might not be n-1 connected to everybody else, but it's large enough that it's going to infinity with n. So then you still, and this would still be the dynamics, right? And now you still have this dv over gn as being your strength of interaction between any neighboring particle and yourself is inversely proportional to dv of gn, which we're saying goes to infinity. So that's again decaying to 0. So you might very well expect that all the things that we said for the mean field may go through in this case, or everything that went through for the complete graph may go through in this setting as well. And of course, it's a little more subtle to show this, but as you can see, it was done much later than the work of McKean and Vlasov. But in fact, you can show in the for particular classes of graphs, different people have looked at under this sort of dense condition, which is that the degrees go to infinity, that you can show that on any finite horizon, you again have this limiting empirical measure going to a determinist quantity, which is in fact coinciding with the law of a particle. And therefore, the empirical measure once again coincides with the mean field limit, because once again, this is mostly governed by the global empirical measure when dvgn is actually large enough that it's going to infinity. Okay, so in particular, though I have been talking on all my pictures about deterministic graphs, one is often interested also in random graphs because connections may not be sort of deterministic, and there might be some probability that you have a certain interaction. And so that's captured by random graphs, either when you don't really know what the graph structure is. That's another reason to sort of use a random graph ensemble and say, well, let me just see if it holds for a large class of random graphs that represent many structures that might be found of particular graph ensembles. And another reason is you might actually have random interactions. So the interaction graph may be actually random. And so in the particular case, one important graph model that is considered is what is called the Erdős-Rényi graph, which is on n vertices, where each edge between distinct vertices is present independently with probability n. That's called GNPN, which was introduced by Erdős and studied by Rényi, and many properties have been looked at in that case. So in that case, NPN tells you what is the average degree, because now it's a random graph, right? So the average degree in the graph is actually the expected degree of a vertex is NPN. And so when we say NPN is going to infinity, it says that you are in a dense regime. So you're suitably dense. And in that case, we say that you would have the same sort of asymptotic independence and a mean field limits. And remember that these limits will again be described by these McKean-Vlasov equation, the same one. And like I said, the key feature is this drift depends on the law of the process. And as I mentioned, if you just look at this, this is just a time inhomogeneous, because in the drift, you have not only dependence on the state, but you also have a dependence on time through the law. It's an inhomogeneous Markov process, but it depends on time only through the law. And so then if you want to write down a evolution for a PDE that the law of XT solves, that's well known. It's called the forward Kolmogorov equation. And that describes the evolution mu. It's a nonlinear PDE in this case because of the dependence of the drift on the law itself. Otherwise, normally for a diffusion, you would just have a linear PDE as a forward Kolmogorov equation. But due to this fact that in this case, you have this insertion of this dependence on the empirical measure, such Markov processes are referred to as nonlinear Markov processes. And they're they're studied by analyzing these associated nonlinear PDEs that you can write down from you. Okay. And so I think these are well known in the literature, and there's a lot of analysis that's done, just pure PDE analysis to understand. And so there's a very good synergy between stochastic processes and PDEs trying to analyze various models. So even though the mean field limit is really well understood, and the McKean-Vlasov equation is more than 50 years ago, there's still research done under various different scenarios and regularity conditions on the drift. And throughout this, I didn't put any diffusion coefficient here, but one can also do that. But I've just tried to keep things as simple as possible to illustrate the main features. Okay, any questions so far? Okay. So the whole thing that I've said is that similar mean fields can also hold for jump processes. Then you get the evolution of the empirical measure can be described by certain nonlinear ordinary differential equations, and also discrete time processes. Then you get certain nonlinear equations. Okay, so what I've explained to you is what's quite well understood. I would say the complete graph is fully understood. Exact conditions on the dense graphs and various classes of dense graphs are still being explored, but the whole point is that they still give rise to the same limit, which is the mean field limit. So one question you might ask is, the whole idea of taking these limits is so that they provide good approximations for the these large systems which you cannot even simulate, or you cannot analytically examine exactly. So this is the plot of the discrete time contact process, which has on its y-axis the probability of a typical particle in state 0. And the blue is a full simulation here, which goes is the lower line. And the red is what is the mean field approximation, or the mean field limit that you would put for this process. And this is on a ring, okay, so just on a cycle graph. And you can see that the mean field performs rather badly. And if you look in the applied literature and in a lot of scientific journals and studies in biology, neuroscience, etc., mean field approximations are used everywhere, and for lack of a better alternative. So when you have a finite graph, there's no sequence, so you cannot determine whether it's dense, sequence, or sparse. But so they just use the mean field approximation, and it's doesn't perform too well. And the same thing holds for many other processes. I'm just showing you the same problem with the discrete time SIR process. Here, the simulation now is the larger one. It's a probability of being healthy versus time with some initial state. And the green is the mean field approximation, which again does badly. Okay. And this is, you can do the same for continuous time voter model. Once again, here, what I'm plotting here is the probability that a particular vertex agrees with, this is in a three regular tree, and this is plotting against time the probability that a typical vertex agrees with exactly two neighbors, okay, has the same opinion as exactly two neighbors. And so once again, you see that this doesn't do too well. And so people in the mean fields have come up with ad hoc approximations saying, oh, the reason this doesn't do too well is you're not taking into account correlations, because mean field approximations assume that the neighboring particles are actually asymptotically independent. So you can do some sort of fix, which is sort of non-rigorous. But even if you do that non-rigorous approximation, it still doesn't do well in many of these cases that PAs, they're called pair approximations. And then, of course, you can look at triplets and quadruplets, but these systems don't really close. And so there's not really a clear understanding of whether those are good enough. And anyway, they don't necessarily do well. And it's not clear when they will do well, if at all. So our goal here is to actually go beyond mean field limits and look at the sparse regime. So what do I mean by the sparse regime? So here we have this complete graph. And now you have a dense graph. This is actually an Erdős-Renyi graph, a sample from an Erdős-Renyi graph with NPN large. This is a sparse graph. So of course, pictorially it's clear, but what I mean by that is that NPN in the sparse case is not going to infinity and it remains bounded, and it's something strictly between 0 and infinity. Okay, so or in general, it doesn't have to be an Erdős-Renyi graph. It's a sequence of graphs whose maximal degree is bounded, or maximal average degree, if it's a random graph, is uniformly bounded in it. Okay, and what we want to understand is, there's been so much work on understanding mean field limits. We should try to understand what is the marginal dynamics of a typical particle in this other setting, in the sparse graph setting. And so there was surprisingly little work on this, and this is an ode to all my collaborators who made this an interesting journey. This is Dan Lacker and Ru Wu, who were former postdocs with me, Ankan Ganguly, who's a graduate student about to graduate, and then several undergraduate students who did various honors thesis projects. So what are the challenges in the sparse regime? As I mentioned, we want to consider the sort of running example of a pairwise interacting diffusion. And in this case, the particles are strongly interacting. Why? Because this dVGN is bounded, right? So the influence uniformly bounded in N. Okay, so for instance, on a 3 regular tree, it could just be 3, right? And you have this influence of your neighboring particle in you, therefore does not diminish as N gets large. And so you don't expect any asymptotic independence of neighboring particles. And so you can't sort of say that, okay, I have these classical limit theorems for independent, and this is almost like that, and I can try to guess what happens. No, so really new ideas are required to understand the sparse regime. Another thing is one cannot now expect a limit by just sending the number of particles. So here, with some abuse of notations, I often use Gn for the vertex set as well, just to not have to introduce another notation all the time. So the size of the graph to infinity, right? Because I could clearly take a 3 regular graph, and then when n is let's say some 10, and then for n is 15, I could take a lattice of that size, and it wouldn't make sense that I would not expect that if I take completely different structures for different n, that there should be any limit, because you do expect the graph structure to play a role. So that's another thing I should emphasize, right? In the dense graph regime, what we noticed is that really the graph structure didn't matter. It was just send the n to infinity. The neighborhood structure was not really important, but as you do expect that to be important in the sparse regime. So now you have to think of what are suitably consistent sequences of graphs. And there's a natural concept when you talk about sparse graphs. We can encode sparsity and the notion of convergence of graphs via a concept called local convergence, or local convergence, introduced by Benjamini and Schramm. And there are also several other monographs, Alderson, Steele, Bordanav, and many other sort of references that can give more insight into this. But it's a very natural notion, which says, but now you look at rooted graphs. So that means a root is a special vertex that you have chosen. So take a graph with a vertex, set V, edge set E, and row, which is a special element of V. And I will assume it's locally finite, which means so this could be an infinite graph, and I assume it's connected. That means there's always a path of a collection of edges that's connecting any vertex to another. And locally finite means all the degrees of the graphs are finite. And so we say that rooted graphs, Gn, converge locally to G if the K neighborhood, in the sense of graph distance, of the limit graph is close to that of all sufficient, the same is isomorphic to the K neighborhood of all sufficiently large graphs. Okay. And so that's the reason why you need this sort of root in both of them, so that you can understand what the neighborhood, it's always the neighborhood of the root. Okay. And so that's a very natural concept. You know, you can see several examples of local weak convergence. So of local convergence, if it's a random graph. So you have a cycle which locally just looks like a line. You have a line graph that converges to an infinite line. You have a one-sided, your root is at this point, then it converges to a semi-infinite line, just to show how the root matters, and it converges to a semi-infinite line with root at the end. Or if you take a tree with a certain fixed depth, and then you increase the depth to infinity, that converges to an infinite regular tree of the same deregular tree. Okay. And then you can also have, okay. So some of the non-trivial graphs that of local convergence is if you take a random regular graph, which is a graph which you take a deregular graph on n vertices. There are a finite number of them, and then you take a random vertex from that. That also converges to a deregular tree. And that is not so obvious anymore, converges locally, because whereas one has a cycles, the other one has no cycles, right? So the deregular tree has no cycles, but the deregular graph does. So that is another case where it's saying that the cycles in a deregular graph are getting larger, because that's why you have this notion of local convergence. Another very important class of graphs for which you have local convergence is an Erdős-Schwenny graph. And in an Erdős-Schwenny graph where NPN is converging to a constant lambda, it turns out that that converges to a limit random graph called a Galton-Watson graph, which is a graph where, you know, which models genealogy. So it starts with a root, which you can think of as an ancestor, and then it has a random number of offspring, which are distributed according to a Poisson distribution with parameter equal to this limiting value of NPN, which is, let's say, some P. And then each of the children, again, independently have offspring with the same distribution. So many, many random graph models, in fact, converge with the root chosen uniformly at random in these finite random graphs. They converge to limit graphs, which are random trees. There's also some notion of random graphs called preferential attachment graphs, and they also converge to a random tree. Okay, I mean, you also have, of course, convergence of finite lattices to lattice, okay, but many random graphs to an infinite lattice, but many random graphs are, in fact, actually random trees. So now you look at sort of local convergence of marked graphs. What we talked about so far was just the graphs themselves. But when you're talking about dynamics, you also need to look at initial conditions. And when you look at initial conditions, then you want to think of them as marks on the vertices of the graph. So you have, and they could be marks on R if you're looking at diffusions. So then you want to have a notion of convergence, and these, of course, initial conditions could also be random, but you have this notion of convergence, which is again very natural, where you say a marked graph, so which is Gn and Xn, converges locally to a limit graph if there is an isomorphism where, because then of course Gn converges to G in just as the local converges locally to the limit graph G, but there should exist an isomorphism for every K, for every finite K neighborhood, such that the corresponding marks are also very close for all large enough n. So given any small epsilon, there's a large enough n such that there's an isomorphism that takes one K neighborhood to the other K neighborhood, and such that then the corresponding marks are also epsilon close. So the isomorphism classes of these marked graphs admit a Polish topology under this convergence. And so that means you can talk about random elements in these graphs. And our goal will be to now understand, just as you have these graphs converging to limit graphs, and you might have these marked graphs with initial conditions, what we really want to understand is when these graphs are marked with solutions to your SDE, then do you have this convergence? Okay, so that's the first thing we want to say, that if you have a particle system on a rooted graph with some initial condition marks, then the result that we had is that if this GNX, the initial conditions marked graphs converge to a limit marked rooted graph, then the dynamics associated with those initial conditions also converges to the limit graph and the dynamics on the limit graph. And in particular, of course, we were interested in typical dynamics. So the typical dynamics on the sequence of graphs, this is the root, rho n always denotes the root, will converge to the limit graph, okay, in the space of continuous functions. And for us, we're just looking at d is equal to 1 for simplicity, which is just continuous functions in R. And moreover, when this convergence happens in a strong sense, which is in convergence in probability, that's what I've written here, which I'm not going to go into the details of, but it's a slightly stronger notion of convergence that also holds for graphs that need not be connected, such as, for instance, a sparse heterogeneous graph. Then you can have also the empirical measure on the trajectories, which is what we were interested in. And now here, I've not put a T here, if you notice, because then this is actually the empirical measure on C itself. So this is the empirical measure of the trajectories, converges to the law of the root particle. So this is the sort of the same that you had in the mean field case, that in fact, the empirical measure does coincide with the limiting law, okay? Okay, there was some related work on just the local convergence for a particular class of diffusions by Oliveira, Rice, and Stollerman as well. And in the jump process setting also, there was work by with Anka and Ganguly in which we show similar results, except here it's much more subtle, because you have to put an additional condition on the limit graph, because it turns out that even well-posedness on infinite limit graphs is not obvious for certain limit graphs that do not satisfy certain properties. So we can come up with counterexamples of it in very simple Markovian dynamics on deterministic trees for which the corresponding jump dynamics is not well posed. So you need to make sense of xgx, and so for that you need to impose some conditions on the limit graph, but this is pretty mild in the sense that it satisfies all the graphs that we were interested in that come as limits of local convergence, such as unimodular Galton-Watson trees and bounded degree graphs. Okay, but the second question that we had is we want to see if we could do an autonomous characterization of the root dynamics, just like we had in the mean field case, which is this wonderful, McKean-Lasov limit. But all we have done here is we've said that we can replace the root dynamics on GN by the root dynamics on a limit graph, which is even larger. So marginalizing an even larger graph is only going to be harder. So that doesn't help with actually autonomously characterizing this dynamics. Now, in the dense regime, once you knew that this had a deterministic limit, you really knew what was happening on the whole system, because the whole system was just driven by the global empirical measure. But here in the sparse regime, the whole system is driven by a random local empirical measure, which is just the points that are coming from the neighborhood, which is not the whole graph at all. And so therefore, knowing what the global empirical measure's limit is does not tell you what the dynamics of x rho n is. So you really need new methods to characterize the dynamics. And as I mentioned, so the local limits of many random finite graphs amongst the vertex are what are called unimodular rooted trees, and unimodularity can be viewed as a way of saying that you are picking the root at random, which doesn't make sense in an infinite set, but it's a notion that can be made precise through something called a mass transport principle. And so it turns out that these local limits of many random finite graphs are actually unimodular trees. So it makes sense to ask about the characterization of marginal dynamics just for these classes of trees. And it turns out in the sparse regime that instead of looking at an autonomous characterization of the dynamics at the root, you should look at the root and its neighborhood. You can't expect sort of an autonomous characterization of just the vertex. So let me tell you what the result is. So for UGW trees, we showed that there is in fact an autonomous characterization. I should emphasize that this was for a particular class of diffusion, this was left as an open problem in the literature, and there was no conjecture even of what the form would be of such dynamics. But we characterize this in terms of local equations. In the diffusion setting, this is work with Dan Lacker and Yogo Wu, and this is work still to be posted with Ankit Ganguly. Okay, so I cannot go into the details of the technical details of what these local equations look like in general, but I will just give you a little bit of a flavor before I conclude. So let's look at the simplest case, which is a two regular tree, which can then just be identified with the line. So this is definitely a sparse graph, like the circle we know converges to this limit. And we can put the root at 0. And then you have sort of your neighboring particles -1. And so this is the black particles here is the neighborhood that you want to understand. And it turns out that the characterization of these can be done by a diffusive equation. So these are independent Brownian motions indexed by 1, 0, and -1. And these are the original B's that we had in the system. And the new thing is that we have this integrals, just like we had with the full global empirical measure in the mean field case. But in this case, we have some integrals with respect to some conditional laws. You don't have to absorb any of the details, but just like we have this integral, like this bx and bxy with respect to mu here, this bracket is again an integral of this gamma t, which is some law which only depends on the past of the process with respect to some corresponding drifts. Okay, so I only want to tell you about these key properties of this marginal dynamics. This law of the marginal dynamics on the root neighborhood can be thought of as a sort of nonlinear path-dependent SDE. So it is non-Markovian, even when the original process is Markovian, the marginal dynamics is non-Markovian, and it can be viewed as an infinite dimensional nonlinear Markov process. So whereas in the mean field case, you have a finite dimensional Markov process, in the infinite dimensional case, you have a nonlinear Markov process, but also the dependence on the law of the process is a little non-standard in terms of certain conditional laws rather than just the law. Okay. And with that, I just want to quickly go. There are some ingredients of the proof. Use a stochastic analysis, some Markov random fields, which try to tell, because we know that we don't have independent trajectories here. You have to understand the conditional independent structure of these trajectories. And then you also exploit symmetry properties of the limit graph. For more details on this proof, you can look at the jump process setting in a talk by Ankit Ganguly on Saturday, April 9th. So I will conclude by telling you how these approximations perform. So numerical results for the discrete time contact process. Once again, I remind you that this was the mean field approximation in red, and the full approximation in blue is the simulation for this. And the green is what you get from the local approximation, which you can see coincides with the full ring. Similarly, for the discrete time process, the green is the mean field approximation, the red, blue in the simulation. And for the voter model that I remember, the continuous time voter model, a certain approximation to the local equations, which are Markovian approximation to the local equations, in fact, performs quite well, the red being the simulation and green being the Markovian approximation. So I will end with that, saying that the goal over here is to try to establish limit theorems for empirical measures and marginal dynamics of interacting stochastic processes on sequences of sparse graphs, to understand better how we can give more principled approximations, because in the literature, mean field approximations are overused even when their applicability is limited. So we're hoping that by studying these processes that we've looked at further, we can understand when more precisely mean field approximations or their refinements are useful, or when one should use these alternative approximations, and also how one can study these new processes that have been introduced, these path-dependent nonlinear Markov processes, in order to analytically get more insight into many specific applications. And with that, here are some references, and I'd like to thank you very much for your attention.
Thank you very much, Kavita, for a wonderful talk. If we could, everybody, A round of applause electronically. Wonderful. So I think there's time for a few questions here for members of the audience. If you have a question, please unmute yourself, and the floor will be yours. We have a few minutes, I think, for a couple questions.
Yeah, so I have a question. I don't know if I'm supposed to keep my video off or not. I think I'm supposed to. So thank you, Kavita. Very interesting. And I know we're going to get more technical details in a couple hours. So I will ask a non-technical question along the lines of Ken's introduction about combining, let's say, science and math. And my question is this: can you give us or give us a good, at least one good story about how these kinds of models have been used with success in science? I know you already mentioned how the mean field model doesn't necessarily predict well what's going to happen, but whether they use mean field models or not, can you give me an example where these models have actually given good applied results?
Yeah,
Kavita,
so,
could you turn on your camera so the audience can see you, please?
sure. Yeah, sure. Yeah, thanks for the question. So this work is been done over the last 4 years or 3 years. And the first thing that we were really happy with is to actually say that it provides, so the examples that I gave of the numerical approximations, to say that if you really want to understand the voter model on the sparse graph, if you want to understand the typical dynamics, you have this way of actually simulating the dynamics. Now, with that, I will put a caveat. The marginal dynamics that we've got is non-Markovian, right? I mean, that is the nature of the beast, that it turns out that on sparse graphs, the marginal dynamics is not Markovian. So of course, to use them, to actually use them as approximations requires some more care. But in ongoing work, so we actually have Markovian approximations, which is at this point still ad hoc, and we're trying to prove in particular classes of examples where we can show that these are good and what are the sort of rates of convergence. So you can actually get error bounds by understanding these dynamical systems, which can be written, by the way, as quite simply in terms of ODEs, explicit ODEs. So imagine that you have this really, really large graph, and you want to study the voter model on that graph. What we're saying is that you can look at sort of ODEs, which are finite number of coupled system of ODEs, which may provide a good approximation. In cases where the limiting dynamics is, in fact, for instance, is a certain kind of Gibbs measure with a particular structure, then we can even get some results on the stationary distribution by looking at the stationary marginal. Maybe the short answer to your question is there's still a lot more work to do to actually look at this general theory on specific analytic results for specific models, which is what our next goal was, which is sort of what I was alluding to when I said this is the tip of the iceberg, and much work remains to further study equilibrium dynamics and to fully exploit these results to gain insight into specific applications. Right now, we've just demonstrated that, sort of through numerics, that these local approximations do well even because you have a limiting theorem, of course, but you need to know that it does well for reasonable n, right? That it's not that you have to go to 10 to the 6 before you see convergence. But we also actually have, with a student of mine, proving convergence rates for a very, very specific model on the cycle. But there's a lot to do here to develop tools to be able to analyze these local equations. And that is very much ongoing because just establishing these results itself took some time.
Yeah, I don't think I was clear with my question. My question wasn't about applications of your results, but applications of these models in the past in applied work. So I know that SIR model is used a lot, for example, but does it in fact give good predictions or useful insights in applied work?
That's what you were asking. Yes. Yes, I believe so. I think that, the Kuramoto model, for instance, has provided various insights about synchronization, synchrony. And that's something that I'm very interested in. I haven't shown you, but even in oscillatory systems, our local equations are able to track. But that's not what you're asking, just the Kuramoto model itself. things about circadian rhythms or things about synchrony has been used for, by looking at coupled oscillators. The SIR model and SEIR models are, there are these versions with SEIR and things like that, are of course approximations. But for instance, if you look at what, if you want to look at refinements of what is the R0 number, which everybody might have read in the newspaper, and I actually have a math co-op, this math outreach program, which I'm doing, which is going to actually explain this to the lay population. But so this R0 number is actually done, computed in this sort of branching sense, but it really means it's a mean field approximation. So if you really have this kind of graph structure and you want to understand better what is really the reproducible, the R0 number for the spreading of an epidemic, you have to be more careful. And there have been, some studies in that direction, and we hope that, we will also be able to shed insight over there. So I do think that they're used to gain insight in many models. I will give a very concrete example, actually, which is not one that I mentioned, because I was focusing more on scientific examples here. But in engineering, for instance, if you look at load balancing, there's something called randomized load balancing. And when you have a bunch of parallel queues, and you have packets that come and they have to be routed to one of the queues based on the states of the queues, so as to minimize, sort of the probability of queues being very large, because queues are typically finite, have finite buffers, and you don't want to lose packets. So these models have actually been used. There's something called the power of 2, where you have a incoming packets, and you choose any 2 queues at random and just go to the shorter of the 2. Now, of course, you could try to look at all the queues and go to the shortest of them, but that's typically computationally infeasible, and it requires too much communication overhead. So this power of 2, of just choosing 2 and going to the shorter of them, was devised as an alternative to have lower communication but better performance. But it has shown this analysis, by looking at this, has shown dramatic improvement in performance. You can show that instead of having an exponential decay, if the job sizes are exponential, you actually have a double exponential decay. And so that led to using this a lot. But then people also studied then what happens if you don't have exponential sizes, but your really more realistic job sizes are not exponential, they're given by some other distribution. Then there are results on whether or not you still expect this performance gain, etc. So yes, I would say that these models are not even an approximation in this case, because this is exactly what you're doing in the engineering setting. This is exactly the routing mechanism that you're using. So, and that's used also in a lot of other engineering models as well. So interacting particle systems in those models are very much quite realistic, I would say, because you can sort of engineer exactly what you're doing, so you know precisely what's being done.
So Kavita, I have a question of a different flavor.
Yes.
As this is an invited dress meant for a very wide audience, I feel like the following kind of question must be asked, right? As the first AAAS-AMS invited speaker, you serve as a role model. You serve as a role model for many different communities, for applied mathematics, for science, for women in science, so on and so forth, for international cooperation. With all of these things in mind, what would your message be, say, to a college student who's thinking about what their career path might be?
Well, I tell any college student that they should really look into, see, and follow their passion, because I think that if you do something that you truly like, then it won't be work, it'll be pleasure as you do it. But that's just a generic advice, not related to science. If it's a person who's actually interested in science, then I do think that I encourage people to get role models to have several different role models. Don't try to get someone who looks exactly like you, or who's exactly from your same ethnic background, or just look at somebody whose values are aligned with yours and who inspire you. I think I've always done that, and I take different qualities from different people. So I've never found a sort of lack of role models, because I've just seen so many inspiring people who have said, oh, I see this person is doing so much for the community. I should also try to do that. This person is mentoring so well. We should try to do that. And so just take that as inspiration and don't get bogged down by not seeing somebody who looks like you or not seeing somebody who duplicates you in some way, but look more into sort of what qualities different people have that could inspire you.
Sorry, wonderful. I forgot to unmute myself. Well, I think we should wrap up. Just a closing. Thank you again to Professor Ramanan for giving the first lecture. And one small message I would like to end this lecture with is the following. COVID has been very difficult on all of us, and we hope that that the future is much brighter. And hopefully the next time we have a JMM, it will indeed be in person, so that we can all get back to the business of mathematics, science, research, all of the above. And let's do our part to restore the value in education and scientific research. So with that, thank you very much, Kavita. Thank you for attending, and have a good day, everyone.
Thank you.